Hello everyone, welcome to EMV Videos. This is my Physics 2212 Lab 1 video lab report on charge tapes. So quick overview of this lab, we will be looking at the electric field interactions between two charged pieces of tape. And the central fundamental principles at play are the momentum principle, defined here as the net vector force being equivalent to the change in momentum per change in time, electric fields, and the electric forces, which we'll look at empirically in just a moment. And the electronic tools used were GlowScript and Python to create a model for this scenario. A few important starting equations are the vector electric field for every point in space defined below, where Q is the charge to the particle emitting the field, and the vector R is the vector pointing from the particle to any point in space. And note here that the constant K is 1 over 4 pi epsilon, which is equivalent to 9 times 10 to the 9th Newton meters squared per coulomb squared. And additionally, we have the vector electric field force acting on every point in space defined below, giving an important relationship between the charge of that observed particle and the interacting field. We'll use this to calculate some simplifications later on. And the goal of this lab is we're looking at two charged pieces of tape, and with one stationary piece of tape, when the other piece of tape is brought close enough to it, the other tape will begin to float. And from Newton's second law, or the momentum principle, we know that no change in momentum in the y direction implies all forces in the y direction interaction must sum to the zero vector. A few notes are the system is a floating piece of tape, starting as everything else in the room and the universe, orientation, positive x to the right, positive y above, and the main sources of force are the other charged piece of tape and the Earth. So two simplifications can be used to simplify the complex interactions. The first one is to assume each piece of tape has the same net charge, and this is overall reasonable because the electrons will spread out across the surface of the tape that are nearly equivalent in size. And the second one, we will be treating each tape as if its charge were located at a single point in the center of the tape, so looking at a point model instead. And we can use this to the formulas introduced previously to estimate the complex interactions by the more simple two-point charge model. So here are some implications from simplifications that we're using now. And as you can see here, we're using the Q observed as the same as the charge of the piece of tape floating, or in this case, the point charge floating. And thus we have a Q squared term in the numerator, as same as before, Q times the magnitude of the electric force from the original charge piece of tape here. And then additionally, we can formulate the magnitude of force acting on the floating tape. And this works because we are correctly assuming we're near the surface of the Earth. And using the momentum principle, we know that the vector sum of these two forces must equal 0, which means their magnitudes are the same. Thus, we can equate these two magnitudes and solve for Q. So here is some experimental data that we found. And the length of the tank was 0.195 meters. The mass of the tape was 195 times 10 to the negative 6 kilograms. Magnitude of the force of gravity we calculated to be 1.911 times 10 to the negative 3rd newtons. Separation distance at equilibrium was 0.06 meters. And with some algebra, we can isolate the charge on the floating tape, shown here, and it was calculated to be 2.765 times 10 to the negative 8 coulombs. And a quick note here, the charge was determined to be positive because the tape was attracted to a negatively charged pen. Thus, we are also able to calculate the number of deficient electrons and the ratio to the number of atoms. So, looking at the coded model that accompanies the experiment, we used GlowScript to calculate the charge of the floating piece of tape with the stated assumptions. And a quick few notes, with the stated separation distance, there are no other parameters other than the charge that are non-constant. So the calculated charge with the function will be the same from the model. If the separation distance were different, we created a function that enables us to find the actual charge. And two pieces of tape were simplified to point charges, and even distribution of charges along the tape allowed for approximately the same charge. And looking at the code now, here is the simulation. We have the top floating charge with the gravitational force in green and the electric force from the blue particle in orange. And a few calculations. Here we see the charges about the same as before. And the difference between them is very small, so we have a good approximation. And here's the code itself. We have a few constants, we have functions and the initial objects, initial values. And this is also linked in the description, also on the page itself if you'd like to look at it later. But essentially, it's translating everything that we have from our simplifications into code in Python. So two concluding questions that we have. So if charge signs between protons and electrons were reversed, the signs of most of our computational equations would reverse, but the interactions between oppositely and similarly charged objects would be the same. In terms of the experiment, tapes would now have a negative charge because the pen would have a positive charge and would still repel each other, allowing for equivalent magnitude calculations. And the second one would be handling the piece of tape as little as possible is essential for this lab, because when the tape comes in contact with another object, electrons must move between them. Because of this movement of electrons, lack of electrons in the tape results in some being transferred to it during contact. Thus, the charge on the tape and the calculations regarding it are altered during the experiment. Thank you for listening to my lab.